some applications later, but maybe also to give you a bit of a practical view. For example, one question was, oh, can we use this for assessing what happens to the solution if we change some bounds in the problem? Yes, you can use these techniques to do that. For example, if we change the horizon of the problem, like the final time, can we assess what is the impact of changing that via these techniques? Yes, you can do that. So anything that you change in the problem, you can, I guess, almost everything you can think about, you can frame it as a parameter that you change and use these techniques to have a cheap way of assessing how will the solution and cost change if I change this parameter. So final time, model parameters, changing bounds, and so on and so forth. And so you don't need to resolve the problem many times to assess the effect of changing something. You can get at least first order picture of what the parameters do to your solutions and cost by using these techniques. All right. Yeah, also if you don't have any active constraints, so all the H would be strictly negative, for example, so the solution is really inside the feasible domain, then A is empty, this disappears, that disappears, and you're back into the case of before. So only the cost and on the equality constraint. So no mystery here. So this is really just an extension of what we saw before. There's no big change otherwise. And yeah, I mentioned that in the KKT condition chapter, but you see this popping up again. When you have strictly active constraints, locally you can look at them as equality constraints. It's completely valid, this reasoning, and you see that appearing in the equation. So in that sense, H of A, all the strictly active inequality constraints, mathematically they will be treated as if they were equality constraints. So H, A, and G have the same, appear in the same way in the structure of the equation. And it's as if H of A was equality constraints. And locally it's true. If the solution is pushing against an inequality constraint, if you change something on the problem, it will stay on that constraint. So it's as if the solution was locked on that constraint. And since it's only once the multiplier, once it becomes 0 or negative, that then you release the solution from the constraint, and then it does not behave like an equality constraint. Any question on that? Okay, let's see a little bit visually what it looks like. Here is a completely made up NLP. I have two variables, W1, W2. I have a nonlinear equality constraint with a parameter P, and then the parameter also enters in the inequality constraints with, like here for example, a nonlinear function of P. There's absolutely no problem with that. As long as the functions you throw in are sufficiently differentiable, there's no issue with having anything you want. So if I solve my problem for different values of P, so here it's P going from -4 to 2, and you have W1 and W2. And so if I apply all these techniques we have seen, here's what happens. So if I'm solving the problem at P equal -3, so I'm solving it here. So I would basically run Newton on my problem, or SQP or something. I get this point here, W1, W2. And then I can form my sensitivities. So what happens here, the mu is 0, the constraint here, this guy, is inactive. So my active set is empty. So if I want to compute my sensitivities, I form this matrix here. I don't have my nabla WHA because I don't have any active constraint. So I form this guy here. And the mu is 0, it will stay 0 until I hit the constraint. So my mu A bar is 0 and will stay there. So that defines my sensitivities, or the Jacobian of my primal dual solution. And I report it here for the primal variables. That's basically this tangent here. So I get this slope here of this red line via calculating that. And I could make a plot for a lambda and mu as well. It would have similar patterns. And here I show you the value of the constraint. So h is minus 0.23 more or less. So it's strictly inactive. And you can then navigate your manifold. So you change p, solve the problem again, and compute always the slope using this stuff here. And so you can really see essentially this slope is telling you more or less what happens to your solution if you change p. So if you solve the problem at this point and wonder, that's about minus 1.5, and you wonder what would the solution look like at minus 2, you have a pretty decent answer from that first order approximation. You could use this slope and this point here to extrapolate what the solution should be if you change p. Of course, it's always first order predictors. So if the here, for example, the solution manifold is like strongly curved, it's gonna be valid only locally. So you still have this limitation, of course. And then you approach this point here. Here h is minus 0.1, and you can probably suspect now what happens at this corner is that the inequality constraint becomes active, so h will become 0 and mu will become non-zero. So this stuff here will change once I pass this corner. So once I pass the corner, mu is non-zero, a is active, I have a single inequality constraint, so now a is index 1. I need to change my system to get the sensitivities. I need to throw in my active constraint, so that I might have my nabla wh here. The mu becomes part of the variables that change, and it changes also the right hand side. But now I get this slope here that matches this side. And so if I was trying to build something at that specific point here, I could actually both calculate that system and the other system and get two different solutions for del w del p, del lambda del p, and del mu del p. And one system would give me that slope here, so this guy here, and this system would give me that one. So in that sense, you could evaluate the system on both active sets that you can have at this point. At this point, you can decide that the constraint is active or inactive. It will not change the solution per se, but it will change the slope. Then your h stays 0 on that side or close to that, and the mu and the w's are changing. Okay with that? So in principle, you could, there is no problem with doing the sensitivities on the left and on the right of the corners. You would get completely meaningful answers. But you have essentially two derivatives at that point. We talk about subgradients in that context. Okay. Now I want to discuss of a bit of an extension of that. So when you play with this type of linear predictor, so again, that's essentially building the tangent at any point on the manifold. And if you carefully keep track of your active set, you can build the slope at every point, and then once you pass the corner, you'll build the slopes on the other side. So there is in principle no problem. Unfortunately, for example, if you solve the problem close to the corner, you get this kind of tangent predictor, or like this stuff will tell you that the slope is this, and once you pass the corner, you basically completely miss the fact that now the manifold will very quickly change to something different, right? So in that sense, when you have to pass corners, this kind of construction will not tell you much about what the solution will do next. Does that make sense? The good news is that there is a way to actually kind of embed the corners into these predictors, and that's by replacing solving simple linear systems by solving QP approximations. So if you understand that as a predictor, so I'm building the sensitivities of the primal dual solution. Say I multiply by a change in the parameters, and that will tell me how the primal dual variables will change accordingly, right? So multiply by delta p, and that tells me how the W and P's will change. If I replace this thing here by basically a QP problem, where I actually basically form essentially a QP for a change in delta P. It kind of looks like the stuff we had in active sets, or in SQP methods, to the difference that we are now trying to form first order expansions of the problem in terms of the change in the solution and change in the parameters. If I do that and I solve my QP for different change in the parameters, so now I'm essentially building delta W as a function of delta P, I get that kind of picture. So what happens here, I would solve my NLP for a given P, that would be this one here. I get a solution W0 and also the primal dual variables. Then at that point, I assemble these matrices, so H and this nabla PW with the Lagrange function and these linearizations. So all these guys, I would build them at that specific point here, at my W and P. And then I play around with this delta P. So I can say that delta P0 here, and then I move P around, so I have different delta P. So P0 is this point here, and if I want to try a different P's, that gives me different delta P's. So I could solve my QP for these different delta P's and get the correction delta W of my W0. And if I do that, the QP will actually be something that looks like a linear predictor, but it will actually also see changes of active sets. If I do it at that point, I get this picture here. So here I get the same stuff as my normal linear predictor, what we have done so far. But then if I go far enough, the QP actually does understand in some way that there is a change of active set coming. So this corner here, it's kind of seeing it as, well, there is a corner coming, but we are very far, so the approximation is not very good. Same here, huh? So the QP sees this corner here as being some corner there far away. If I move around again, navigate my solution manifold, you see that as we approach the corner, the QP becomes better and better at seeing this corner coming. So here at this P0, I solve the problem, get W0. The QP is predicting this change in the active set and this corner in this form. So this thing here is a change of active set inside the QP. And so on and so forth. And as you get close to the corner, actually the QP sees this thing very accurately. So if you now ask from your QP to form a prediction, so if I solve the problem here at this P0, I get this solution. They'll give me a prediction of what would be the solution if I solve it, for example, here, now, here. By doing a single QP, you would predict here, and the NLP would bring you here. So it's pretty close. Same here. The prediction, instead of having the linear predictor that would bring you up here, using the QP, it actually brings you on the other branch of the solution manifold. So it's pretty effective at calculating this or seeing these corners coming. Same here, you pass the corner. And as you move away from the corner, the prediction becomes not very good. Here you don't see the corner anymore from the QP, it's too far away. So in that sense, the QP is also a linear predictor. It's building lines, right? But it also can detect these non-smooth changes in the manifold and do that quite accurately when you're close enough. Okay with that? Yeah. Okay, how can we use this kind of predictor in the context of parametric NLPs? So again, imagine you solve your NLP for a given P, call it P0, and you get the solution W0. And now without resolving everything and recomputing all these things, you are trying to get the prediction of what would happen if you solve the NLP at a new parameter. And you can see this new P as a perturbation, call it delta P, so this P minus P0. You insert that delta P in the QP, you solve the QP, you get the delta W, and then you use this delta W to correct your W0. You see that idea? So here we go. I solve for P0. That's my new P, the blue one. And the predictor is bringing me to this orange point. And you see that it's pretty much, it's almost at on the NLP solution. So it's a pretty good prediction. And I can move forward like this, solving the NLP, for example, here. And my QP predicts the next solution to be there, and so on and so forth. If I pass the corner, the QP is still good at predicting what will happen around the corner. So if I move from this P to that P, the QP is capable of predicting that there's a corner coming and the next solution will be actually here. So it remains accurate throughout the corners. Okay with that? So
does it matter which way you're moving?
No, you could move back. It doesn't matter at all. So this is really, this thing is building a first order approximation of your solution manifold. So you can move anywhere you want. What matters is that you don't move crazy far, because then the linear prediction is getting lost a little bit. You still have curvature in your real solution manifold. So up here, I mean, this is not a bad prediction per se, but it's a bit off, of course. Yeah, so from that point, solving the NLP at that point, then building your QP, you could have a pretty good picture of what is coming around. So that's it can be valid for a pretty large set of parameters, actually. Okay, so this is already suggesting where it's going. So one thing that people do in using this approach, there's only one application you can have is following a path. So you can imagine that your P is changing continuously in time, and you're trying to keep up with that P with your NLP. An example of application is an MPC, for example. In that context, P, the parameters, would be the initial conditions you receive from your observer, right? And then you need to resolve an optimal control problem with initial conditions that change always a little bit. Hopefully they are not crazy different than what they are supposed to be, but they are a bit different. So in that sense, it's exactly this kind of things. So your nature is in some ways navigating P. Maybe it's moving back and forth around, and you're trying to keep up with that. So you're trying to always follow that path as accurately as you can. And in that context, having good predictors is really helping you. And we talk about path following, it's really about how if P changes all the time, I'm trying to keep up with that P. I update my solution all the time to stay on the manifold. And we'll use these IDs, typically either linear predictors or QP predictors. So linear predictor would build this thing here, and if you use a QP, you also start getting the corners. So yeah, it's used again in a number of things. Real-time NMPC is an example, but again, all these things, multi-level optimization, homotopies, and so on, you can use these techniques. Okay, so So you can imagine that I'm throwing at you new values of p all the time, and just to make it simple, we'll always move along this line, but in reality it could be moving around, and it could be a higher dimensional space. But we're always trying to keep up with the new p coming. So it's changing all the time, and you want to get back on the solution manifold all the time using these techniques. And here is, for example, a naive way of how you can do that. So you've solved the problem, for example, at that point. So that gives you a z, and now you receive a new p, and maybe you will consider that this new, give the initial guess for this new p, the one you got before. So your w lambda u, the last one you got. You use that as initial guess, you form a new QP for this initial guess, and try to use that QP as a essentially as a way of taking an SQP step towards the solution. We'll be essentially solving here, and I will keep this Z as an initial guess for the next one, and then I will do an SQP step to try to catch the manifold. And then that's maybe all the time budget I have. Then maybe I'll receive a new P, and whichever I received after one SQP step, I'll reuse it as an initial guess for the next one, and so on and so forth. So you can imagine that context, that reality is running and you have to keep up with that. So that will be, you use the previous solution, build the QP that you would use in an SQP step, get an update for delta W and lambda and mu, return that, and then you already receive the next P, so you have to take your next SQP step. So you could think of this as essentially doing SQP, but instead of iterating to converge, you all the time receive a slightly different problem. So P changes a little bit, and you're basically always running SQP and trying to keep up with the P's changing. Does it make sense to you? Yeah? Okay. Here's what could happen. So you start from a P, and that's the next P plus. So that will be what happens if you deploy this algorithm. So here it's working really well. It's not necessarily a surprise. Here the solution manifold is almost linear, so it's not necessarily surprising. Here you lose a little bit, so your SQP step brings you not far, but not exactly on the manifold, and so on and so forth. So this kind of approach is working fairly well, but it's not really perfect. And the reason here is that you're basically forming the next QP using P plus, but you still use an old initial guess. So you're right on the parameter when you form these matrices and vectors, so this GH and these gradients here, but you're a bit wrong on the initial guess. So that. Is the new solution by one SQP step? Say it again. Is the blue point the new solution? Yes, exactly. So that's redeploying this guy. So you start from being on the manifold, and then you change P to P plus. You form the QP again, but you form it based on the red point, and you take the QP, and that brings you here. Yeah. So at some point you're a little bit inaccurate. So one way of using this predictor approach is to say, okay, this is the solution for P. Now I need to solve at P plus. So I could make a prediction of what my W lambda and mu's will be if I change my parameters, and then use that prediction to form the new QP. So it's the prediction will not be exact, but it will help me forming a QP at a better point. And that could look like this. So you receive W lambda mu from the previous point. You also know where it was formed. You also receive P plus. So you form your delta P, and you form a first order predictor of what the solution will be according to this change of P. So you get something like this. That's the QP we looked at before. And these guys are all formed at the red P. That gives you an update of the primordial variables. So this returns delta W and the new lambda and your new mu. So you use this to correct your Z. Then you form the QP again on this new point. It's not the exact point, but it's a good prediction. And then you solve that QP here to make a full correction of the step. And I show you here, I actually compare what we did before. That's the round marker with this thing here, that's the star. So here, they are both agreeing on what should happen next. But once we pass the corner, for example here, this version here is basically nailing exactly the manifold, while this guy is a little bit off. So doing this preemptive correction using the predictor allows you to form the QP at a much better point, and then and get a very good solution for the next point. Okay with that? Okay, there's a price to pay here because you are doing 2 QPs for getting your next point. So instead of doing 1 QP as we did before, you need an extra one. So that's extra expenses. It would still be a great idea to do that if solving the QPs is fairly cheap, for example, compared to linearizing the system. Forming these matrices is a bit expensive. That's often the case actually in optimal control. It may be a good idea anyway to do 2 QPs. When we do these things, so that's a prediction of what delta W or how the W change for a change in P, and that's what we would call a correction. That's essentially the prediction is probably not bad, but it's not perfect. So you're basically doing something like a one-step SQP to try to bring back your point on the solution manifold, right? So prediction, correction. You would use this term or hear these terms a lot in when people talk about path following. So we have this picture. There is the predictor. That was the first QP in my algorithm before, and the correction, that's the second QP. That's the classic stuff we use to do SQP. Huh? The interesting thing is you can actually merge them into a single one by essentially summing up these terms here, these guys and these guys. And then you have the so-called predictor corrector as a QP. So you have terms coming from delta P changing. If delta P changes, it will dictate a change in W. And you have these terms that essentially boil down to your solution W not fully satisfying the KKT conditions. So you can think of this in these terms in some ways. If delta P is 0, these purple terms disappear. And if you run this QP, you basically get an SQP step. So you're trying to get closer to your solution. Use a delta P, then you change delta W because P has changed. So the purple stuff is basically creating a response in the QP for changing the parameters. And the blue stuff is creating a response in the QP for not having solved the problem to full convergence yet. So you have correction of the solution, prediction for changes in the parameters. All right. Yeah, so if P plus equals P, that means delta P is 0. Huh? Then it's a classic SQP step, purely a correction of the solution. If you use P plus different than P, so you have a delta P, then you also have a prediction effect coming from the purple terms. That will be that's typically what people do in the end. prediction correction path following, where you essentially receive the previous solution, z of p. It may not be a fully accurate solution. Maybe it's not really on the solution path. You receive a new p plus. Then you calculate your delta p, how p has changed from the previous problem, and you form this QP here with the correction and prediction. Solve it, and that gives you a correction delta w and the lambda and mu's, and you update your z for the p plus according to this correction. You do that, and then the next round you already get a new p plus possibly. And if you do that, you will get this kind of effect where you see the bubble is following the manifold not too badly.
This is still one step?
Yeah, it's really applying this this algorithm. So it's here I take fairly long steps in P. So to see if you take shorter steps, you're like too close to the manifold to really see a difference. So here that's a fairly aggressive update of the parameters, and yeah, you could compare this to the other methods. This is typically fairly efficient at following the manifold. It's a bit less efficient than the double QP actually for some reasons that have to do with where you linearize the point, but it's pretty good anyway. Okay with that? So this kind of techniques is, for example, used in real-time MPC. When you P is changing initial conditions in your problem, and you essentially do a single QP for per an MPC sampling time. Yeah, okay, that's a good thing. We could try to do the same and remove the predictor from the stuff. So you could have like a more naive approach where you just do the correction, and here is what happens. So it's in the same configuration. It's much harder to follow the manifold if you remove the prediction effect. You can compare that to the previous one. So that was with the predictor and without. We're a bit all over the place. I'm very aggressive in the parameter updates here, but there you see what happens. So the predictor really does play an important role in keeping track of the manifold.
How does that differ from the first, the naive approach?
Yeah, that was a naive approach essentially. Yeah. No, sorry. That's not exactly true. This one, you use the H and G and nabla G formed at the last solution. In the naive approach, I was actually reforming these guys on the new P plus. Here I don't. So the H, G, nabla G, they are formed on P and Z, the ones you get from before. That's why it's also not behaving as well. If you also reform these guys on the new P plus, it would look a bit better actually. Okay with that? Yeah. So you have yeah, it's a bit of a jungle. You have a number of different ways you can use these tools to follow a path, and it's actually not completely obvious depending on exactly what you want to do, what is really the most efficient thing to do. So it's about really understanding these tools and then decide where you want to place the computational time and how you want to be effective. Okay, so all this stuff has to do with really inspired from SQP techniques, so and active set methods with this active sets changing in the linear predictors and solving QP. So it's very SQP-like thinking. And we looked at interior point methods as well, of course, and all these sensitivity IDs, you can apply them directly on interior point methods as well, and that's also very useful to understand, in my opinion. Yeah, I'll discuss that a little bit. And in some ways, in the interior point context, it's actually a little bit easier to think about these things, but you also lose a few things. So we can look at it. So these are the KGD conditions with the modifications we usually do in interior point method. So introducing these slack variables on the inequality constraints, and then the compatibility conditions, they read like S times mu is 0. And then you want S and mu to be positive. And then you have the interior point style conditions. You relax this the corner with a tau, and then you want these guys to be strictly positive. And so these four equations, they define your W, lambda, mu, and S completely. And these are things that should hold at the solution. That's for a given tau, of course. So when that's an interesting thing to chart actually. We didn't look at this yet. So remember that this tau is essentially doing this smoothing in the compatibility conditions. So we have this corner in the normal KGD conditions, and with the tau, we actually create something smoothed with this guy here. And now we're talking about solution manifold, so how the solution evolves as P evolves, and we have discussed essentially these corners you get from changing the active set. So changing the active set means that we navigate through the corner of this condition here, and on that side we are going around the smooth corner of the KKD conditions. What happens then to the solution manifold? It looks like this. So these are, for a given problem, the parameters on this axis and the primal solutions W1, W2 of your problem. And you can see here, that's the exact solution with the corner. There's an active set change here. And if you chart the solution manifold as obtained from these conditions for different values of tau, you also have a smoothing effect on the corner of the solution manifold. So the fact that we smooth the corner here in the KKD conditions also means that we smooth the corner here in the solution manifold. So you have this effect. And the larger the tau, the more off you are with respect to the solution manifold, and the more smooth you are. Okay with that? So as tau goes to 0, you would basically not see the difference between the solution manifold and the corner. And it's really coming from this observation. I remember the solutions you get from this system of equation, the difference between this and that is in the order of tau. So put tau to close to 0, and the difference will be close to 0. So the difference between these curves here and the real solution is in the order of tau. Having said that, so these equations define W, lambda, mu, and S. So I can apply the implicit function theorem on that. I can look at W, lambda, mu, S as functions of P implicitly given by these equations, and I can declare that these guys are my big R. Z is now my collection of variables, including the S, and I just throw in all my equations and then simply apply my implicit function theorem on that. The usual stuff, del Z del P given by del R del Z minus 1 del R del P. And as usual, when I form del R del Z, I get my KKD matrix, no surprise. So we've seen this guy in the interior point methods. That's the usual matrix you get. And as usual, you will use Newton to solve this the linear systems involving this matrix factorized. Once you're done, you can reuse this factorization to build del Z del P. So no problem here. And that's the same story as before. It's completely or almost free to compute the sensitivities. You just need to assemble this guy and use it in the factorization or with the factorization of the matrix. And there you get a linear predictor. And here there's no like QP predictors to talk about because we have smooth KKT condition. So there's no like subgradient appearing when we go around changes in the active set, because we actually have a smooth manifold here. So the derivative del z del p, it exists everywhere here. There's no non-differentiability in the solution manifold. That's really coming from the fact that we smoothed the KKT conditions. So if you have a solution at a given p and for a given tau, it's always depending on tau, you can form the solution at a different p by using a linear predictor. Well, del z del p is built using this equation. Okay, an example. So go back to this manifolds. If I build a tangent predictor on this red guy, it's very smooth. So the advantage is that the tangent predictor will be pretty good throughout. The next one, same story. So here is just tau that has changed, and I can solve the problem at different p's and build the del z del p and get these different things. The interesting thing is, so this is for tau is 10 to the minus 10. Now we're getting close to machine precision. But the IFT will still give you all what you need. So it will still build linear predictors without having to deal with active set or non-active set. You just throw this stuff inside your IFT and everything will work. Now, of course, I said there's a price to pay for this simplicity in some sense, and that here, from this construction, you don't get the this linear predictor that sees the corner. So this effect we were having from the QP, building the QP and with the active set, well, building the QP with linearized constraints, we don't have this picture from this predictor. This is a purely tangential predictor without, it is never going to create corners and see it coming. So in that sense, at very small tau, the linear predictor can be quite inaccurate around the corners anyway. So if you do path following, it can be good to do the path following at values of tau that are not overly small. Okay with that? Nowadays, when we do path following, we often use these approaches, I would say, mostly because they are much easier to use. And if, for example, if you use IP-opt and you want to do path following, it's a very good idea to use this construction. The only thing you need to be careful about is, that's a practical remark. So if you use IP-opt without doing anything special in the options, IP-opt will choose itself the tau it's using. It will mostly pair it with the accuracy you're asking in a solver. So you don't know what tau will be. And once you build your predictor, you need to select the tau, and that's not necessarily obvious what to use if you don't know what IP-opt has used. So what we do when we use IP-opt and linear predictors is that we force IP-opt to exit with a specific tau. You can do that. You can, in the options, say, okay, here is the accuracy at which you solve the KKT conditions, and the tau you will exit with is, for example, 10 to the minus 2, or 3, or 10, whatever. And it will respect that. And then you know exactly on what manifold IP-opt is navigating. Because if it's choosing itself where it wants to be, then this thing may change around, depending on where it's exiting. Okay. I have a few more slides. I think we'll finish that in the afternoon. Take a lunch break now.